Good evening, and welcome to a EuroConnect News special report. We are living through what future historians may regard as the most transformative period in our understanding of the cosmos since Copernicus placed the Sun at the center of our solar system. But this revolution is not one of gentle refinement, it is one of radical upheaval. The universe, as we have understood it for decades, is breaking apart before our very eyes. The James Webb Space Telescope, now completing its second year of unprecedented observation, has not merely added chapters to our cosmic story. It has torn pages from the textbook and forced us to question the most fundamental assumptions of modern physics. What we are witnessing is not incremental progress, but conceptual crisis, a beautiful, terrifying, and exhilarating moment where everything we thought we knew about the cosmos is being rewritten in real time. Let us begin with what should not be. In March of 2024, an international consortium of astronomers published findings from the JWST Advanced Deep Extragalactic Survey JADES that sent seismic waves through the world of cosmology. They identified 6 massive, fully formed galaxies whose light has traveled for over 13.4 billion years to reach us. We are seeing them as they existed a mere 500 to 700 million years after the Big Bang. The staggering fact is not their distance, but their maturity. These celestial cities, designated with clinical names like Galaxies 13 and CERS 93316, contain stellar populations equivalent to our own Milky Way galaxy. Our galaxy took over 10 billion years of gradual mergers and star formation to assemble its current form of roughly 200 billion stars. Yet JWST shows us galaxies of similar stellar mass already shining brightly, when the universe was less than 5% of its current age. This discovery strikes at the very heart of the lambda-cold dark matter paradigm, the standard model of cosmology that has guided our understanding for 30 years. According to this model, the early universe should have been a primordial soup of dark matter and hydrogen-helium gas. Gravity would have slowly pulled this material into small, chaotic proto-galaxies over hundreds of millions of years. These building blocks would then, over the course of billions of years, merge hierarchically to form the majestic spirals and ellipticals we see in the local universe. JWST reveals this timeline to be catastrophically wrong. The galaxies it sees are not fuzzy, irregular blobs. They show clear, evolved structures, rotating disks, central bulges, and in some spectra, the telltale signatures of supermassive black holes already weighing millions of solar masses. Dr. Erica Nelson, a leading astrophysicist on the Discovery team, described it as finding a fully grown adult in a kindergarten class photograph. The laws of physics, as currently formulated, simply do not permit such rapid and efficient galaxy formation. Simultaneous to this crisis in galaxy formation, cosmology faces another, equally profound contradiction that threatens to unravel our model of cosmic evolution. We cannot agree on how fast the universe is expanding. This number, the Hubble constant, is the most critical parameter in all of cosmology. It defines the age, size, and ultimate fate of our universe. For over a decade, 2 supremely precise methods have returned stubbornly different answers, creating what is known as the Hubble tension. The first method, championed by Nobel laureate Adam Rees and his team, builds a cosmic distance ladder. It starts with pulsating stars called Cepheid variables in our galactic neighborhood, whose intrinsic brightness is precisely linked to their pulsation period. By measuring their apparent brightness, we can calculate their distance. These Cepheids are used to calibrate distances to nearby galaxies that host a special class of exploding stars, type Ia supernovae. These standard candles are even brighter, allowing us to measure distances to galaxies billions of light years away. By observing how fast these distant galaxies are receding from us, their redshift astronomers derive an expansion rate. This local, or late universe, measurement consistently yields a value of approximately 73 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. This means a galaxy 100 megaparsecs away is receding from us at 7,300 kilometers per second. The second method uses the baby picture of the universe, the cosmic microwave background radiation. This is the afterglow of the Big Bang, released when the universe was just 380,000 years old and cool enough for atoms to form, allowing light to travel freely. The European Space Agency's Planck satellite mapped the subtle temperature fluctuations in this radiation with exquisite precision. These fluctuations are the seeds of all future structure, the slight overdensities that would grow into galaxies and clusters. By feeding this primordial snapshot into our models of cosmic evolution, which include the effects of dark matter, dark energy, and the known laws of physics, cosmologists can extrapolate forward 13.8 billion years to predict what the expansion rate should be today. This primordial or early universe method gives a value of 67 kilometers per second per megaparsec. The difference of 6 km/s/mpc seems small, but in the high-precision world of modern cosmology, it is a yawning chasm. The probability that this discrepancy is due to random measurement error is now less than 1 in 3.5 million, a 5.6 sigma tension. This is the gold standard for a discovery in particle physics, but here it signifies a crisis. New data from the Dark Energy Spectroscopic Instrument, which has mapped millions of galaxies to trace the large-scale structure of the universe, has only confirmed the higher expansion rate, deepening the puzzle. This tension suggests a fundamental flaw in our standard model, lambda CDM. Several revolutionary possibilities are on the table. Perhaps dark energy, the mysterious repulsive force causing the acceleration of expansion, is not a constant, cosmological constant, as Einstein conceived, but a dynamic field that has changed strength over cosmic history. This field, dubbed quintessence, could have been weaker in the past, altering the expansion history and reconciling the early and late measurements. Another idea is early dark energy, a transient burst of repulsive energy in the universe's first 100,000 years that would have subtly altered the sound waves frozen into the CMB, throwing off the Planck measurement. More exotically, some cosmologists suggest we live in a local cosmic void, an underdense region of space billions of light years across. In such a bubble, gravity's weaker pull would make nearby galaxies appear to be fleeing faster than the true global average, creating a biased local measurement. The most thrilling possibility is that we are seeing the first empirical evidence for entirely new physics. A fifth fundamental force, interactions between dark matter and dark energy, or a modification to Einstein's theory of gravity on the largest scales. The Nancy Grace Roman Space Telescope, launching in 2027, is designed as a Hubble constant detective, deploying multiple independent methods to finally break this cosmic deadlock. For most of human history, astronomy has been the science of light. We have built ever larger telescopes to collect photons across the electromagnetic spectrum. But in the last decade, we have gained a new sense: hearing. The detection of gravitational waves, ripples in the fabric of spacetime predicted by Einstein, has opened an entirely new window on the universe. The LIGO, Virgo, and KAGRA observatories, following major upgrades, are now in their fourth observing run. Their sensitivity is so extraordinary that they are detecting the catastrophic mergers of black holes and neutron stars not as rare, front-page events, but as routine occurrences. The detection rate is approximately 1 to 2 per day. In April 2024, the consortium announced its 200th detection. We have moved from the era of discovery to the era of population statistics. We are now studying the demographics of compact objects, their mass distributions, their spins, their rates across cosmic time. This tells us how these monstrous objects form and evolve, whether from the collapse of massive stars or from earlier mergers in dense stellar environments. The most profound gravitational wave discovery of the past year is one we can feel more than see: the gravitational wave background. Using nature's most precise clock's millisecond pulsars, the spinning neutron cores of dead stars that beam radio waves with metronomic regularity consortia, like NanoGrav in North America and EPTA in Europe, have detected a low-frequency hum permeating the cosmos. This is not the loud chirp of a single merger, but the collective chorus of millions of pairs of supermassive black holes, each millions to billions of times the mass of our Sun, orbiting each other in the centers of distant galaxies. As these cosmic giants circle one another over millions of years, they emit gravitational waves that stretch and squeeze the spacetime through which the pulsar signals travel, causing infinitesimal, correlated timing delays. This hum confirms that galaxy mergers, long theorized, are a dominant, ongoing process shaping the universe. It also presents a puzzle. The signal's strength suggests black holes may be more massive, more common, or merge more efficiently than our models predicted. The future of this new sense lies in space. Scheduled for launch in 2035, the Laser Interferometer Space Antenna LISA, a joint ESA-NASA mission, will be the first gravitational wave observatory in space. It will consist of 3 spacecraft flying in a perfect equilateral triangle, 2.5 million kilometers on each side, trailing behind Earth in its orbit around the Sun. Laser beams connecting these craft will measure distance changes 100 times smaller than an atomic nucleus. Free from the seismic noise of Earth, LISA will detect gravitational waves at frequencies too low for ground-based detectors. It will hear the final inspiral and merger of supermassive black holes, events that shake spacetime for millions of years. It could detect the remnant gravitational waves from cosmic inflation, the universe's violent birth spasm. It might even find exotic relics like cosmic strings, theoretical defects in spacetime from the early universe. LISA will transform gravitational wave astronomy from a novel detection method into a primary tool for exploring the most energetic events in cosmic history. To comprehend the grand story of the universe, we must first understand our own galactic home with forensic detail. The European Space Agency's Gaia mission is performing nothing less than a galactic autopsy. For over a decade, it has been constructing a 6-dimensional map of nearly 2 billion stars within the Milky Way. For each star, Gaia records not just its position, but its 3-dimensional motion through space, its brightness, its color, and through complementary ground-based spectroscopy, its detailed chemical composition, its stellar DNA. This vast dataset enables a new field, galactic archaeology. We can now read the history of the Milky Way written in the motions and chemistry of its stars, reconstructing events that occurred billions of years before our planet formed. The biography Gaia reveals is one of relentless violence and cosmic cannibalism. Chemical fingerprinting, comparing the precise ratios of elements like iron, magnesium, and europium shows that stars born together from the same gas cloud share a distinct chemical signature. This analysis reveals that vast populations of stars in our galaxy's outer halo carry alien chemical imprints. They were forged not in the primordial Milky Way, but in other, smaller galaxies that were later torn apart by our galaxy's immense gravity and assimilated. At least 6 major merger events have been identified. The Gaia-Enceladus merger, which occurred approximately 12.5 billion years ago, was a cataclysmic event where a dwarf galaxy roughly 1/4 the mass of the infant Milky Way was consumed, dramatically altering our galaxy's structure and star formation history. The more recently identified Pontus merger, occurring 8 to 10 billion years ago, added another substantial stream of stars. Current estimate is staggering. Up to 50% of the stars in our galactic halo, the diffuse, spherical swarm of ancient stars surrounding the main disk, were born in other galaxies. Our Milky Way is not a solitary island universe. It is a galactic Frankenstein's monster, assembled over eons from the devoured remains of its neighbors. This violent past prefigures an even more dramatic future. In approximately 4.5 billion years, the Milky Way will collide with its largest neighbor, the Andromeda Galaxy. Based on precise measurements from Hubble and Gaia, we know this collision is inevitable. Detailed supercomputer simulations show it will not be a cataclysm of colliding stars. The distances between stars are far too vast, but a majestic, slow-motion gravitational dance lasting hundreds of millions of years. The 2 beautiful spiral structures will be shredded by tidal forces, their stars flung into elongated streams before settling into new orbits. The galaxies will pass through each other, separate, and then fall back together to merge permanently. Their central supermassive black holes, Sagittarius A** in the Milky Way, and a much larger counterpart in Andromeda, will sink to the new common center through a process called dynamical friction, eventually merging in an event that will release more energy in gravitational waves than all the stars in the observable universe emit as light. The final product will be a giant elliptical galaxy, a smooth, featureless football-shaped collection of stars, the final resting form for most large galaxies in the dense environments of galaxy clusters. Our night sky, from the perspective of any surviving descendants, will be utterly unrecognizable. All these structures, the stars, the galaxies, the clusters are composed of ordinary matter, protons, neutrons, and electrons. This is the universe we see, touch, and are made of. Yet, overwhelming and convergent evidence from the past 50 years tells us this familiar matter constitutes a mere 5% of the universe's total mass energy content. The remaining 95% is dark and mysterious. Approximately 27% is dark matter, an invisible substance that interacts via gravity but does not emit, absorb, or reflect light. We know it exists because without its extra gravitational glue, galaxies would spin apart, galaxy clusters would fly away from each other, and the patterns of light from distant galaxies warped by gravitational lensing would make no sense. The European Space Agency's Euclid telescope, launched in July 2023, is humanity's most ambitious mission to map this dark architecture. Over its 6-year survey, Euclid will image 1/3 of the sky, measuring the shapes and positions of over 1 billion galaxies with exquisite precision. Most of these galaxies will show tiny, systematic distortions not due to flaws in the telescope, but because their light has been bent by the gravitational fields of the vast, invisible webs of dark matter lying between them and us. This phenomenon, called weak gravitational lensing, allows Euclid to construct the largest three-dimensional map of the dark matter cosmic web ever created. This map is not a curiosity. It is a critical diagnostic for dark energy. By observing how the dark matter web has clustered and grown over the last 10 billion years, cosmologists can infer the strength and nature of the repulsive dark energy that has been working against gravity's pull. Is dark energy a constant force, or has it evolved? Euclid's first dark matter maps, expected in late 2024, will provide crucial new constraints. But what is dark matter? The leading hypothesis for decades has been that it consists of weakly interacting massive particles, WIMP's hypothetical particles, that would interact only through gravity and the weak nuclear force. Dozens of ultrasensitive experiments, housed in deep underground laboratories to shield them from cosmic rays, have spent years waiting for the telltale recoil of an atomic nucleus struck by a passing WIMP. Despite reaching sensitivities that would have detected many theoretical models, the result has been a profound and growing silence. This null result has forced a broad reconsideration. Candidates now include axions, ultralight particles, sterile neutrinos, or even primordial black holes formed in the universe's first second. The lack of a direct detection has also reinvigorated the long-standing alternative theory of modified Newtonian dynamics, or MOND, which proposes that our equations for gravity require modification on the scale of galaxies, eliminating the need for dark matter particles entirely. The next generation of laboratory experiments, astronomical surveys like Euclid and JWST, and observations of colliding galaxy clusters will serve as the ultimate jury in this cosmic courtroom drama. Amid these grand cosmological crises, a more intimate and ancient question presses upon us. Are we alone? The James Webb Space Telescope has begun to transform the search for extraterrestrial life from philosophical speculation into a rigorous branch of analytical chemistry. Its first major exoplanetary target has been the TRAPPIST-1 system, a compact family of 7 roughly Earth-sized worlds orbiting a small, cool red dwarf star just 40 light-years away. In 2024, JWST successfully performed transmission spectroscopy on several of these planets. As a planet transits or passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. Different molecules in that atmosphere absorb light at specific fingerprint wavelengths. By analyzing the spectrum of the missing light, JWST can decode the atmospheric composition. The results are groundbreaking. TRAPPIST-1b, the innermost world, appears to have little to no atmosphere, likely a bare, scorched rock. But TRAPPIST-1e, which orbits squarely within the star's habitable zone, where temperatures could allow for liquid water on a rocky surface, shows a clear spectroscopic signature of carbon dioxide. This is not evidence of life. CO2 can be produced by geological processes like volcanism, but it is proof of principle. For For the first time in history, we have analyzed the air on another Earth-sized world in the habitable zone. We are reading the atmospheric composition of a potentially habitable alien world. Even more provocative is the case of K218b, a mini-Neptune, or sub-Neptune world about 2.6 times Earth's radius and 8 times its mass, orbiting a red dwarf 120 light-years away. JWST data revealed a hydrogen-rich atmosphere containing significant water vapor, methane, and carbon dioxide. Most controversially, the data contained a tentative signal consistent with dimethyl sulfide, or DMS. On Earth, DMS is produced overwhelmingly by marine phytoplankton. While the DMS detection is far from confirmed and abiotic chemical pathways cannot be ruled out, the finding has electrified astrobiologists. K218b is now theorized to be a Hycean, world, a planet with a deep, global liquid water ocean beneath a thick, hydrogen-rich atmosphere. While utterly alien compared to Earth, such an environment could, in theory, maintain a stable liquid water layer and host microbial life. JWST is teaching us that the gallery of potentially habitable environments may be far more diverse than our own planet's template. The next great leap will be from analyzing filtered starlight to seeing the world itself. The Nancy Grace Roman Space Telescope, launching in 2027, will carry a revolutionary instrument called a coronagraph. This device uses a series of precisely shaped masks and deformable mirrors to suppress the blinding glare of a host star by a factor of 1 billion, allowing the faint, reflected light of an orbiting planet to be detected directly. Roman's goal is to take the first pictures of planets similar to Earth around our nearest stellar neighbors. We will not see continents or clouds. The planets will be single pixels of light, but the color and brightness variations of that pixel over time can reveal the length of its day, the presence of oceans, clouds, and perhaps even seasonal vegetation changes. This will pave the way for the Habitable Worlds Observatory, a NASA flagship concept for the 2040s, designed from inception to search for atmospheric biosignatures, like the combination of oxygen and methane on dozens of Earth-like worlds. The ancient question of whether we are alone in the universe may be answered within our lifetimes. Cosmological crises revealed by JWST, the Hubble tension, and the nature of dark matter and dark energy are, at their deepest level, symptoms of a more fundamental problem: the lack of a theory of quantum gravity. For over a century, physics has been split into two magnificently successful but incompatible domains. Einstein's general relativity describes gravity as the curvature of spacetime, perfectly explaining the cosmos on large scales: planets, stars, galaxies, and the expanding universe. Quantum mechanics describes the other three forces: electromagnetism, and the strong and weak nuclear forces governing the subatomic world of particles and fields. Unifying these two frameworks into a single theory of everything is the greatest unsolved problem in fundamental physics. The leading candidate for such a unification is string theory. It posits that the fundamental constituents of reality are not zero-dimensional point particles, but tiny, vibrating one-dimensional strings or multi-dimensional branes. The different vibrational modes of these strings correspond to different particles and forces. Gravity naturally emerges from this framework. However, string theory requires the universe to have more than the familiar 4 dimensions, 3 of space, 1 of time, typically 10 or 11. The extra dimensions are compactified, curled up at scales a billion times smaller than an atom. The specific geometry of these extra dimensions determines the laws of physics, the masses of particles and strengths of forces in our observable 4-dimensional world. One profound implication of combining string theory with cosmic inflation is the multiverse. The string theory landscape suggests there may be an astronomical number, perhaps 10 circumflex 500, of possible stable configurations for the extra dimensions, each corresponding to a universe with different physical constants. Cosmic inflation, the theory that the universe underwent a period of hyperexpansion in its first split second, would naturally generate countless such bubble universes from the primordial quantum foam. In this vast multiverse, our universe, with its specific constants fine-tuned to allow for stars, planets, and life, is just one bubble among an infinite froth. This provides a potential scientific explanation for the puzzling fine-tuning of our universe. If every possible set of laws exists somewhere, it is no statistical surprise that we find ourselves in one compatible with our existence. The multiverse has moved from philosophical speculation to a testable prediction of leading cosmological models. Scientists search for evidence in the cosmic microwave background, looking for imprints of collisions with other bubble universes, or in subtle statistical anomalies in the distribution of galaxies that might betray our universe's local conditions. Faced with a universe that grows more baffling and awe-inspiring with each discovery, one might reasonably ask, what is the human role in all of this? We are temporary, fragile assemblies of atoms, products of a 4 billion-year evolutionary experiment on a speck of dust orbiting an ordinary star in the unremarkable suburbs of a spiral galaxy that is itself one of 2 trillion galaxies in the observable universe. Our entire history, from the first cities to the launch of JWST, has unfolded in a cosmic eye blink. And yet, we have developed the capacity to look back 13.4 billion years to the first galaxies, to hear the echoes of black holes colliding a billion light-years away, to decode the atmospheric chemistry of worlds orbiting distant stars, and to ponder the quantum nature of spacetime and the possibility of a multiverse. Every single advance in cosmology is a testament to human curiosity, ingenuity, collaboration, and our relentless, almost defiant drive to understand our place in the grand scheme of things. The technological byproducts of this quest permeate our modern world. The charge-coupled devices that first digitized starlight now sit in every smartphone camera. The algorithms developed to clean cosmic microwave background data underpin modern machine learning. The need for lightweight, high-strength materials for space telescopes has driven advancements in engineering. But the deeper value is existential. Cosmology provides the ultimate perspective. It shows us our planet not as the center of creation, but as a fragile, beautiful, pale blue dot suspended in a vast, dark ocean of space. From this cosmic vantage point, our terrestrial conflicts, politics, and divisions are revealed as the affairs of microbes on a mote of dust. This is not a message of nihilism, but of profound unity and responsibility. The same laws of physics that govern the spinning galaxies and the expansion of space govern the processes of life on our planet. The carbon in our DNA, the oxygen in our lungs, the iron in our blood all were forged in the hearts of stars that lived and died long before our sun ignited. We are not separate from the cosmos. We are a conscious, thinking part of it. We are the universe's way of knowing itself. The crises in cosmology, the impossible galaxies, the irreconcilable expansion rates, the dark, unknown majority are not signs of failure. They are invitations. They are the universe challenging us, daring us to think more deeply, to question more fundamentally, to imagine more boldly. They are the signposts pointing beyond the boundaries of current knowledge. We stand at the threshold of a new golden age of discovery. The James Webb Space Telescope is just the opening act. The Roman telescope will hunt for dark energy and Earth-like worlds. LISA will open the gravitational wave spectrum. Giant 30 and 40-meter ground-based telescopes will dissect the atmospheres of exoplanets in unprecedented detail. Each new tool will bring new mysteries, new crises, and new, unimaginable insights. Our story is written into the cosmic story. It began with hydrogen and gravity. It produced stars, galaxies, planets, and on at least one world, life that could look up and ask, why? The answers we seek will not just tell us about the cosmos out there. They will tell us about the nature of reality, consciousness, and our unique place within it. The universe is not a static, solved puzzle. It is a dynamic, evolving, and unfinished symphony of matter, energy, and information. We have only just begun to learn how to listen. The greatest discoveries do not lie behind us in the solved equations, but ahead, in the brilliant, confounding light of the unknown. The journey has just begun, and it promises to be the most extraordinary adventure in the history of human thought. For EuroConnect News, this has been our report from the edge of understanding. Thank you for joining us on this journey through the breaking universe.